So let's finish up 12.1 with our significance test, but first let's do a confidence interval problem just for review. So two AP students decide they want to investigate the effect of sugar on the life of cut flowers. So they put teaspoons or tablespoons of sugar in 3 vases and try to see the freshness in hours of carnations. So we want to construct and interpret a 99% confidence interval for the slope of the true regression line. Remember, our confidence interval is our point estimate, B, plus or minus our critical value, T star, times the standard error of the slope. Our B is this number right here. It's kind of hard to read, but 15.2. So we plug that in. Our T star, we do our inverse T of alpha divided by 2, so 0.01 divided by 2, so 0.005, comma, degrees of freedom, which is, there are 12 vases, so we subtract 2, our degrees of freedom is 10. So inverse T, 0.005, comma 10. On both calculators we get the same thing of 3.169. Standard error of the slope is right here under the standard error of the coefficient for this one. This is our slope. So 1.943, we substitute it in, 15.2 plus or minus 3.169 times 1.943, we get 9.04 to 21.35. So how we interpret this? We are 99% confident the slope of the true regression line between tablespoons of sugar and hours of freshness of carnations is between 9.04 and 21.35 based on our sample. So that should be of sugar, not and sugar. It's the same way we interpret our confidence intervals before, no different. Alright, now we're going to look at a t-test. So our conditions for the inference, most of the time we suppose they're met because we're going to be using the Minitab read-off. But if we're not, it needs to be random, residuals are normally distributed, and a linear relationship. So if it's not linear, we can't do this. Our t-score is b minus b naught over the standard error of the slope, which is just our point estimate minus our parameter over standard deviation. But again, we're not going to calculate that. It's going to be given to us by that Minitab output. And usually b naught or beta naught is 0. Find the p-value by calculating the probability of getting a test statistic this large or larger in the direction. So use the t-distribution with degrees of freedom n minus 2. We use t-CDF. Again, we're not going to really have to use this. So we have 3 different ways it can be. We can check to see if, first of all, our null is that beta equals 0, or that there's no linear relationship. The slope is 0, there's no relationship. Our alternate could be 3 different things. Right-tailed, meaning beta is greater than 0, or a positive linear relationship. Beta is less than 0, a negative linear relationship. Or just that beta doesn't equal 0 and it's any linear relationship, positive or negative, it doesn't matter, just that there is a linear relationship. Didn't really copy too well. That's what our graphs look like. So we follow phantom. So we're going to do it on this problem. Infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. So, kind of bogus, they snap a rubber band on the sole of a foot and cause the infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the children's IQ at age 3 years using the Stanford-Binet IQ test, just a standard IQ test. The table below contains data from a random sample of 38 infants. So 38 minus 2 is our degrees of freedom. When you see a list of data values on an exam question, don't just start typing in the data. You might not need it. Notice we have all this data, but they give us all these graphs. We don't need it. So first we look here. It's kind of linear. We look at our residual plot. There's no pattern. We look at the residual normal probability plot, and it is linear, so we have met our conditions. So what is the equation of the least squares regression line, predicting IQ at age 3 from the number of crying peaks? So predicted IQ equals 91.268, that's our A. Our B, our slope of our sample, is 1.4929 times the cry count. Interpret this: the slope for every one cry peak a baby makes, his or her IQ goes up 1.4929. The y-intercept: if a baby had a 0 cry count, his or her IQ would be about 91.3. Is that realistic? Maybe, maybe not. It's outside all of our x values as we see here, and maybe not. It goes down to 9, so that could make sense. Explain what the value of S means in this setting. Remember, that's our standard deviation of the line. So if we use a least squares regression line to predict IQ based on cry count, on average we'll be off by about 17.50 points on the Stanford-Binet IQ test. So that's all review. Now here's the new stuff. So we follow our phantom. Our parameter is beta, which is the slope of the true regression line. Can't stress that enough. The true regression line between cry count of a baby and IQ. So our null is always beta equals 0, that there's no relationship. And here we want to see there's a positive linear relationship, so beta is greater than 0. So it's right-tailed. Is it random? It says it was random. So we have that going for us. Is it a linear relationship? Yeah, we have the residual plot here. And is the residuals normally distributed? Yes, because we have a normal probability plot. So our assumptions are all met. It is a linear regression t-test. That's our n. Our t is given right here. And our p-value is right here. So we don't have to calculate anything. Everything's given right to us. So t is 3.07, p-value is approximately 0.004, which is very much less than our alpha of 0.05. So we have sufficient evidence to reject the null, ergo we can support the claim that there is a positive linear relationship between crying counts and IQ in the population of infants based on our sample at alpha equals 0.05. So very similar to what we've been doing. They give us the t, they give us the p, they basically give us everything. We don't have to worry about too much of anything.